Hello to everyone. In this video, let us see what are the impurity defects and also properties of solids. So see here, first let us see impurity defect. That means if any foreign atom or ion present in a crystal lattice that causes which one impurity defect, or by the addition of impurity to the which one here pure ionic crystal, that also causes which one here impurity defect. And here due to that impurity defect, what happens, let us see here, and how that takes place in any an ionic crystal lattice. Let us see here. For example, if we consider that which one here NaCl. NaCl when mixed with MgCl2 impurity. Now that addition of MgCl2 to NaCl crystal, that means addition of impurity to a pure crystal is known as doping. So now here when MgCl2 added to NaCl, we can see there is a defect, formation of a defect. Why it will takes place? See here. If the valency of the impurity ion is not same with as a host ion valency, then it causes which one defect? Here the impurity ion means magnesium, its valency is +2. But here the Na plus, the host ion valency is +1. So these are not the same. Then we see the formation of which one here defect. So like that, if the impurity ion valency is not same as that of host ion valency, then a defect is generated. So now how that defect is generated, let us see here. For example, if 1 Mg+2 ion added to 1 NaCl, now that Mg+2 ion equals to the 2 number of Na plus ions with respect to charge. So that means 1 Mg+2 displaces 2 Na plus ions from the which one, that crystal lattice. So like that, first we have to remember one thing. The number of univalent ions displaced is equal to which one? Charge of the impurity ion added to that crystal. That means Mg+2 is having +2 charge. So it displaces 2 univalent, that means 2 Na plus ions. So like that, first we have to remember one thing. The number of univalent ions displaced equal to the charge of the impurity ion doped to that pure crystal. Okay, then now of the two vacancies, as 1 Mg+2 displaced 2 Na plus ions, in NaCl crystal we can see 2 vacant sites. Now in between these 2 vacant sites, one site is occupied by this Mg+2 and another site will remain vacant. That is called cationic vacancy. So now here when 1 Mg+2 doped to 1 NaCl, now here the number of Na plus ions displaced are 2, but the number of cationic vacancies, how many, means 1. So we can generate a formula for this type of questions. What is the formula? The number of univalent ions displaced is equal to which one? Charge of the impurity ion. And another one, the number of cationic vacancies generated equals to charge of impurity ion -1, because here only one cationic vacancy is present. So now let us see some questions related to such type of doping. Okay, now what is the question here? For example, for 1 mole of NaCl, for 1 mole of NaCl, now 10 power minus 5 moles of 10 power minus 5 moles of SrCl2 is doped. Now the first question is here, number of Na plus ions replaced. Number of Na plus ions replaced is dash. So now, as our description here, the number of Na plus ions displaced equal to charge of impurity ion. That means if one SrCl2 is doped to NaCl, one, that means what happens here, one cationic vacancy, of course that is later we can discuss, 2 Na plus ions have been displaced for one SrCl2. And similarly, for 10 power minus 5 moles of Sr plus 2 ions, how many Na plus ions are displaced means 2 into 10 power minus 5 moles. So see here, 1 Sr plus 2 displaces 2 Na plus ions. That means 10 power minus 5 moles Sr plus 2 displaces 2 into 10 power minus 5 moles Na plus ions. Here the displaced Na plus ions number is present in moles, but sometimes the question they may give not in moles. How many number of Na plus ions have been displaced? We know that 1 mole of any substance contain 6.023 into 10 power 23 species. Therefore, 2 into 10 power minus 5 moles of Na plus means how many number of Na plus ions. Therefore, number of Na plus ions displaced equals to 6 into 10 power 23. Of course 6.023, don't worry, let us take 6 only. 6 into 10 power 23 into 2 into 10 power minus 5. That means 12 into 10 power 18. 12 into 10 power 18. So these are the number of Na plus ions displaced. Now, how many cationic vacancies are created? Now, number of cationic vacancies created, what is the formula we have given? Charge minus 1. That means, if one Sr plus 2 is doped to 1 NaCl, as Sr plus 2 is having plus 2 charge, the number of cationic vacancies how many means 1. And similarly, if 10 power minus 5 moles of Sr plus 2 is doped to NaCl, therefore number of cationic vacancies equals to that, which one, 2 minus 1 means 1, that means we can get which one, 10 power minus 5 moles only. If you want to determine in number instead of moles, 10 power minus 5 into 6 into 10 power 23. That means 6 into 10 power 18. Number of cationic vacancies are created. So like that, the question might be related to number of Na plus ions displaced or the number of cationic vacancies. And sometimes that question they may give in different way. So now what is that question? See here, when 1 mole NaCl is doped with 1 mole NaCl is doped with which one? 2 into 10 power minus 2 mole percent of SrCl2. Number of cationic vacancies. Number of cationic vacancies are dash. Here they have given not moles, mole percent they have given. By using mole percent, first let us calculate number of moles. So now number of moles of SrCl2, or we can write Sr plus 2 also. 2 into 10 power minus 2 mole percent means divide with 100, we get 10 power minus 4 moles. So this is the number of moles of which one here? Sr plus 2 ions. Now if 2 into 10 power minus 4 moles of Sr plus 2 ions are added, now they create how many here? How many number of, that means how many Na plus ions displaced means, first let us write this. Number of Na plus ions displaced. Number of Na plus ions displaced means we have to write which one? Charge into number of that Sr plus 2 ions. So 2 into 10 power minus 4 moles. That means we get 4 into 10 power minus 4 moles. These are the Na plus ions displaced with respect to moles. But if you want to determine number of Na plus ions displaced, 4 into 10 power minus 4 into 6 into 10 power 23. Sorry. 4 into 10 power minus 4 into, okay, 6 into 10 power 23. So these are the number of Na plus ions displaced. And if the question is related to how many cationic vacancies, how many cationic vacancies means here, what we have to do here? That 4 into 10 power minus 4 moles, but from that we have to decrease one number na. So 3 into 10 power minus 4 moles. So like that much cationic vacancies are created. So this is regarding which one? Impurity defects. Okay, then after this we go for which one? Properties of solids. So solids properties majorly classified into two types: electrical properties and magnetic properties. Electrical and magnetic properties. So now let us see what are electrical properties. Based on electrical properties, solids are classified into four types. The first one is here insulators. Insulators means the solids in which conductivity is in the order of 10 power minus 22 to 10 power minus 10 ohm inverse centimeter inverse. They are called as which one here? Insulators. And then the second type is here conductors. In conductors, the conductivity is in the order of 10 power 3 to 10 power 8 ohm inverse and centimeter inverse, in this order. And the third type is here semiconductors. In case of semiconductors, the conductivity is in the order of which one here? 10 power 4 to, or we can write 10 power minus 6 to 10 power 4 ohm inverse centimeter inverse. And another fourth one, superconductors. The solids which are having zero resistivity and infinite conductivity, those are called which one? Superconductors. So these are the types of solids based on which one? Conductors. In that, let us see first conductors. Conductors actually of two types: electronic conductors and electrolytic conductors. In electronic conductors, conductivity is due to movement of electrons, and in electrolytic conductors, conductivity is due to movement of ions. And here the metals can conduct electricity either in solid state or also in aqueous solution state, and the conductivity of metals depends on number of valence electrons per atom. Conductivity of metals depends on number of valence electrons per atom. Okay, then after that, in case of conductors, as temperature increases, conductivity decreases. Why? As temperature increases, like this, if you consider this is a metal wire, as temperature increases, inside you can see vibrations, not outside. Inside that electric wire, we can see the vibration of atoms. When the atoms are vibrating in zigzag way, it is somewhat difficult for the flow of electrons. So due to that, in case of conductors, as temperature increases, conductivity decreases. Now let us see the semiconductors. Of course, in case of semiconductors, intrinsic and extrinsic two types are there. Intrinsic semiconductor means within the increase of temperature, that semiconductor act as a conductor. That type of conductors are called intrinsic semiconductors. Example, silicon and germanium. Within increase of temperature, there is a increase in conductivity. And also, by adding some impurities to them, to such type of semiconductors, we convert them into conductors. That type of conductors are called extrinsic semiconductors. Okay, now addition of impurities is known as which one? Already we discussed that, doping. Addition of impurities is known as doping. So by doping, we convert semiconductor into which one? Conductor. In that, two types of semiconductors are there. N-type semiconductor. First one is N-type semiconductor, and second one is P-type semiconductor. Two types of semiconductors are present, N-type and P-type semiconductor. Let us see what is N-type semiconductor here. Now, for example, if you consider silicon or germanium, 4th A group elements, when these are doped with 5th A group elements. Now what happens here? If you consider silicon geometry, as it is a 4th A group element, it is having 4 bonds around each silicon. If the silicon is doped with 5th group elements like phosphorus or arsenic, some of the silicon atoms are replaced with which one? Phosphorus atoms. And phosphorus, as belongs to 5th A group element, it has 5 valence electrons. 4 valence electrons are participated in bonding, but 5th electron remain as a free electron. 5th electron remain as a free electron. And due to the movement of that free electron, now this silicon conduct the electricity. But the conductivity is due to negatively charged electron. So now this is known as N-type semiconductor. But in this, while giving the answer, we have to observe the question clearly. What is that difficulty? I will explain here. First question. If silicon is doped to phosphorus, what is the type of conductor formed? Means it is not the answer N-type. that is p type, because here I have given silicon doped to phosphorus, not doped with phosphorus. That we have to observe. So now that means final conclusion is, if fourth A group element doped with an element which has group number higher than the fourth A group, then that will give which one? N-type semiconductor. When silicon doped with higher group elements, it gives which one here? N-type semiconductor. We have to remember that thing. Okay, then let us see p-type semiconductors. What are the p-type semiconductors? P-type semiconductor means here, consider the same silicon as example here. When silicon is doped with aluminum, aluminum means third A group element, that group is less than that of silicon group, means fourth A group. Now some of the silicon atoms are replaced with aluminum. Now here we know that aluminum as belongs to third A group element, it has 3 valence electrons. That means here one valence electron is short for bonding, and that will present as a hole, or we can indicate with positive charge. And here also we can indicate with positive charge. Now but what happens? The electron present in adjacent atom now moves into this hole. Now we can see positive charge here. And here also if electron of silicon moves into this aluminum, now we can see the positive charge here. Thereafter from this silicon, electron moves to that adjacent, we can see positive charge here. But actually here electron is moving from one place to another place, but it looks like a movement of positive charge, but actually which is moving means electron. But whatever it may be, here this electrical conductivity is generated due to the positively charged hole. That's why only these conductors are called p-type semiconductors. That means if silicon doped with an element which has a group number less than that silicon, that will produce which type of semiconductors, means p-type semiconductors. So these are regarding which one here? N-type and p-type semiconductors. Okay, then after that here let us see which one? Magnetic properties. So based on magnetic properties, solids are classified into 5 types: paramagnetic, diamagnetic, ferromagnetic, ferrimagnetic, antiferromagnetic. So first let us see which one here? Diamagnetic. These are repelled out from the magnetic field, and in this all are paired electrons are present. Those are examples for which one? Diamagnetic. Examples: NaCl is one of the examples of which one here? Diamagnetic. NaCl, benzene, those are come under which one? Diamagnetic. Okay, then paramagnetic. Paramagnetic means these are weakly attracted into that magnetic field. And examples for paramagnetic: oxygen and NO, nitric oxide. Okay, then ferromagnetic. Ferromagnetic means these are strongly attracted into the magnetic field. And of course, in the absence of magnetic field in the substance, the magnetic domains are present irregularly. Magnetic domains are present in irregular arrangement. But whenever that ferromagnetic compound placed in a magnetic field, all these magnetic movements are aligned in one direction, and that become a ferromagnetic compound. And even in the absence of magnetic field also, it can't loses it ferromagnetism. Examples: iron, cobalt, nickel. Those are examples for which one? Ferromagnetic. Okay, then after that, antiferromagnetic. Antiferromagnetic means here what? The magnetic movements are, that means here parallel and anti-parallel magnetic movements are equal in number. That means the magnetic movement is mutually cancelled. So such type of compounds are called antiferromagnetic compounds. Examples: nickel oxide, manganese oxide. And then ferrimagnetic. 1 minute. Okay, ferrimagnetic means here the magnetic movements present in parallel and anti-parallel are in unequal number. They are in which one? Means unequal number. For that, examples are here. Which one? Okay, we can write here Mg3O4 and another one here. Okay, not Mg3O4. Let us take Fe3O4, MgFe2O4, ZnFe2O4. These are examples for this one. Okay, with this magnetic properties have been completed. Okay, bye.